Okay, welcome to our lesson on the physics of climate change. Now the goal in this lesson is to talk about why it is that carbon dioxide and some other gases like methane make the world hotter. Or also, do they make it hotter? Are things more complicated? Now, while 95% of scientists believe that releasing more carbon dioxide makes the world hotter, and this is a problem, there are many politicians and members of the general public who do not believe this. So we're going to talk about some of the arguments on both sides and try and really understand what's going on here. So let's start off with the real basics. What determines the temperature of the Earth? So here's a simple diagram of the Earth. And the middle of the Earth is very hot. It's got all the lava in it and magma that's produced actually by radioactive decay of uranium. But that's pretty much irrelevant for the temperature of the surface unless you're standing on top of an active volcano. The amount of heat leaking up through the ground is very small, and it's completely dwarfed by the heat coming in from the sun and infrared radiation going out. So the temperature of the surface of the Earth is controlled by these: sunlight in, infrared out. If we get more sunlight in, the Earth gets hotter. If we get more infrared out, it gets colder. And you can do a very simple physics calculation to work out what the temperature of the Earth should be. What we're going to do here is assume that the Earth is a perfect black body. It absorbs everything that lands on it and radiates as a pure Planck law black body. This is unrealistic. There are clouds, atmospheres and so on, but let's just go with the simple model. Assume you have basically a lump of coal orbiting the sun at our distance. Now the energy in is equal to the solar constant, which is the energy per unit area of sunlight at our distance from the sun, which is 1361 watts per square meter, and that can be measured from spacecraft. And that hits the Earth. It hits flat on at the equator and at a glancing angle near the poles. But to work out how much energy in total comes in, you can replace the Earth with a disk facing the sun of the same radius, because everything that hits this spherical surface will hit this disk. And it saves you having to do some sort of integral over the curved surface. So energy in is solar constant times pi r squared. How about the energy out? Well, in the simple model, we're going to assume that the Earth is entirely at one temperature. Again, unrealistic. Once again, we're going to ignore clouds. Unrealistic, but let's run with it. So in this case, the Earth will be radiating infrared radiation from its entire surface area. So that's 4 pi r squared. And we're going to use a Stefan-Boltzmann equation. So A sigma T to the fourth, that's the Stefan-Boltzmann constant and the temperature in Kelvin. And that's the heat going out. So if we set it equals S pi r squared equals 4 pi r squared sigma T to the fourth, and solve, we end up with the Earth being at an average temperature of 278 Kelvin, or 5 degrees C. Which is not bad. It's a little bit colder. The average temperature of the Earth is actually more like 14 degrees, but not too bad given all the assumptions that came in here.